Great. So for this first talk, part of the plan for these first two talks, the one I'm giving now and the one that Ori is giving after this, is to sort of overview some of the themes that come up as we think about behavioral models in the context of computational economic systems. And so I wanted to sort of reach back over a number of papers that I've been involved in that have illustrated this theme, including some recent case studies that we've been looking at. And so this idea of behavioral agents in algorithmic environments, and this is going to cover a number of projects with joint work with some fantastic colleagues listed here on the slide. When I think about algorithmic environments that we experience, in some sense, like most of what we do on the online world is mediated algorithmically, right? So when we, consume movie recommendations, it's because some algorithm has computed some feature vector based on our past behavior, and it's using that feature vector, that stylized representation of us to, create an environment in which it's recommending content, right? The same thing when we scroll through a social media feed, our past history of what we clicked on, what we dwelled on, what we looked at, who we messaged, is again going to some feature representation. And of course, as time has gone on, algorithms have moved out of the online world and they've moved into the offline world where people, began to notice analogies, right? When you apply for a job, in some sense, your resume is also a tabular representation of your past work and life experiences that we could then, give to either a sort of, a hiring committee of humans, now often assisted by some algorithm or computational method that's also making some kind of a prediction about you, right? The same for college applications, where to deal with just, the total volume of applications, we now see more and more cases where people are using algorithmic assistance. And so again, we see people, with their past history, the features we build about them, and any, behavioral effects that went into that now being evaluated as part of this algorithmic pipeline, right? So there's sort of a common template to all of this, right? Which is an individual getting mapped to a set of feature vectors, being passed to a decision maker, be they human or algorithmic, which then makes some kind of a prediction about them. And so this is the first kind of what you might call algorithmic environment I want to talk about. And we see this both in what you might call high stakes offline applications, right? The ways in which these are being used now for things like hiring decisions and admissions decisions, like on the previous two slides, also in the areas of credit, in the criminal justice system and medicine. And then on the earlier slides, what you might call these high volume online applications, right? Whether you'll engage with specific content, ads, or political messages, whether your post should be flagged in some way. And, often the first category is called high stakes because it matters to any, each decision, each hiring decision or admissions decision matters a lot to one person. With the online applications, you could say it doesn't really matter whether you were shown this one news article or not. But I think we've learned over time that we take 100 billion of those decisions each day, whether people see different news articles or others, and it can add up to something that is very consequential, right? Which is like the formation of public opinion, as an election approaches. And so in aggregate, that too is high stakes, but the granularity is very different. And so one question in sort of the theme of this workshop is, to what extent do these algorithms need to model the behavioral effects at work? What goes wrong when we don't? What can we try to fix if we do? Now that's one kind of algorithmic environment. I want to talk about a second one just for motivation. This is not the algorithm sort of making predictions about you and serving you content necessarily, but rather it's sort of algorithms serving as partners and interleaving their actions with ours, right? So the fact that, generative AI systems are now in fact actually called, co-pilot systems, sort of evokes the idea that you and the generative AI system are sitting there, your actions are being interleaved for writing or for coding. When we imagine, sort of a future world of increasingly active autonomous, autonomous interventions and things like driving, we again imagine our actions interleaved, between ours and the algorithms and interactions. And in some sense, if I go back to the high stakes applications, we see a similar thing, which is, if a medical AI system is making a prediction about you, it's often really a human doctor interleaving their actions with a machine learning system that's making those predictions. And so, on the one side, we ask, what's the effect on the patient that there's a prediction being made about them? On the other, we ask, what's the impact on the profession of medicine or the workflow of the doctor that their actions are now being interleaved in this way? Here, too, we could ask the same question. To what extent should we be modeling the behavioral effects going on? Okay, so that's kind of sets, an extremely broad context for what I wanted to think about. And in that context, I'll talk about sort of three sort of points along the way, which sort of try to serve as a kind of introduction to some of the things that, I think have been going on in the space, certainly some of the projects I've been involved in. The first is going to go back to some early work that Sigal and I did, which sort of takes the environment as abstract, right? What happens when I just imagine an agent planning in a state space, as we often see in, sort of basic algorithmic problems? And what happens if we add behavioral bias? And then how might we sort of imagine computationally modifying the environment to help behaviorally limited agents? Middle part of the talk, I'll do a sort of theoretical case study on how these behavioral effects, sort of building on the first part, how certain kinds of behavioral biases affect people's consumption of social media feeds. In particular, here the bias is more about impulsivity and the way in which agents might regret actions in retrospect. And finally, I'll talk about a computational case study, which will be appearing at iClear this year, building on this line of work that I've been doing with Ashley Anderson, Sid Sen, Kareem Hamadeh, and Reid McElroy-Young on human algorithmic interaction in chess, and some of the ways in which we can think about algorithms working with the cognitive limitations that human chess players have. Okay, so that's kind of a overview of what the plan is. So let's talk about a first behavioral bias, which will sort of inform a number of the other biases we talk about, which is present bias, right? The idea that an agent thinks about the relative costs and benefits of its actions differently in the present time period than in all future time periods, right? There's a very long history of this in behavioral economics, dating back, to work in the 50s and 60s. David Laibson and others, building models of quasi-hyperbolic discounting in the 1990s. And it became this mechanism in which you could think about properties of people's planning behavior that are hard to explain by other means, right? Things like procrastination, the way in which we put off tasks that we should be doing now, and things like task abandonment, right? The sense in which we, buy the gym membership now, but don't actually go to the gym later. And so when Sigal and I began looking at this, now roughly 10 years ago, we were sort of curious because each of these, models often came with its own sort of intricate, ingenious story about sort of how present bias would manifest itself in different cases. And we were wondering if there was a framework where we could just analyze these scenarios mechanically, right? Where you could actually have something that was sort of so structured that you could actually quantify over possible scenarios, and in that way kind of ask general questions about what does it mean to be in an environment? Like, what is an environment? And so our proposal there was to think about an environment as really the traversal of some state space, right? So as in a sort of planning problem, I have an agent in a collection of states. Maybe the agent starts at state S. They're trying to get to state T, where they would claim a reward. And there's a cost on the edges, right? So in this example, the agent's trying to get from S to T, where they can claim a reward of 13. They can either take the upper path and pay 2 plus 7, or they could take the lower path and pay 3 plus 6. Actually, they're kind of indifferent because they're both 9, both of which would be worth it to claim the reward of 13. And our proposal was that to introduce present bias is a very simple way to introduce present bias and actually recover many of the effects that you see in this literature, which is to simply say the present step looks different from all the other steps that are going to follow. So imagine I'm solving the shortest path problem to claim a reward. I'm only going to continue if the reward exceeds the cost I expect to pay. But the agent has this behavioral bias, which is they think of the present as particularly painful, right? I don't want to do work now. I want to put off work till later, right? Work in the future seems reasonable to contemplate, but work now seems particularly burdensome. And so from the given node I'm at, say node S, all the immediately outgoing edges have their costs multiplied up by some factor B greater than 1, right? So imagine in this example, B is 2. So the agent sits here and it says, I could either go the upper root or the lower root. The upper root is 2 times 2, because B is 2. So this 2 looks like 4 to me because of my present bias. So 4 plus 7 is 11. The lower root looks like 2 times 3 plus 6 is 12. So now I actually prefer the upper root, right? Us looking back, no, the total cost is 9 in reality, but perceptually, this one looks like less. Okay, so I take the upper root. It looks cheaper. I get here, now this looks like not 7, but 2 times 7, which is 14. It no longer seems worth doing the reward, so I actually give up. Right? And so we see very simply in a situation like this, why you might get things like task abandonment, right? The way in which, full of inspiration, you start writing a 50-page survey paper that you plan to submit, and you get 20 pages into it, and then you get busy with other things, and it feels like too much work, and you stop. And it's sort of like, that can't be rational. Either you should never have started, or you should have finished, but writing 20 pages that you never do anything with cannot be the optimal solution. But we see even this very simple agent is going to engage in that behavior because you get to the midway point and suddenly, because of your present bias, things look different. And we could help the agent. We could delete state A and say, well, if I just delete state A, then actually everything works out, because now the agent says, well, that's not available. There's only this one path, which looks like 2 times 3 plus 6 is 12. That's worth the reward of 13. And I get to this intermediate node and I actually continue all the way. Okay. Now, so this idea that I can help agents by taking away choices that they have, that's going to be a theme that I'll come back to, because a lot of the ways in which algorithmic interventions might help people is through this process of choice reduction. And we see choice reduction even in our everyday lives, right? So, if you've taught a class or if you've taken a class, then we know that, one way to assign homework would be at the beginning to say, okay, class, you have 8 problem sets over the semester. Here are all of them. Please pace yourselves and hand them all in by the end of the semester. And as anyone who's ever tried that knows, this becomes a complete disaster because, as human beings, we're not very good at pacing ourselves over 12 weeks to do 8 distinct things. And so everything piles up toward the end. Suddenly you can't finish everything. There's lots of, figuring out sort of how to deal with these emergencies. The model that we have actually almost mechanically, produces that effect, and also proposes the intervention that we all do, which is even if we know what our 8 problem sets are going to be, we say the first one's due in week 1, next one's due in week 2. We force people, we constrain their actions so that they're able to do this, right? And again, a model like this is able to explain this kind of thing, right? So this is now a more complicated graph that tells the story of, should you give people the option to do all the problem sets, available right at the beginning? Imagine in this story, a 3-week short course where you have to do 2 projects. If you finish the course, you get a reward of 16. Doing the projects, each week that you're in the course without doing a project costs you 1. Doing 1 project costs you 2. Maybe doing both in a week costs you 9. And I could represent your progress through the course with time moving from left to right. You doing the projects moves from top to bottom, right? So the state Vij means we're, V21 here means we're 2 weeks into the course. You've already done 1 project. And so you have to figure out, like, when should I do the projects in the class? They're both available at the beginning. And so given the numbers I put in, again, with B equals 2, you say, well, I could do both of them right away. That would cost me, what, like 2 times 9 to get to here, and then 1 plus 1, I get to the end of the course, right? So this whole path looks like it would take me 20, right? 2 times 9 to do it right away. Or I could do 1 project now, that's 2 times 4, plus another 4 plus 1, that's 13. Or best of all, how about I don't do anything now? And then I'll do the next 2 projects in weeks 2 and 3. That sounds good. So the present bias agent decides to do that. They look and they say, well, actually, I'd have to do a project now. That's 2 times 4 plus 4. That's 12. It's still worth the reward of 16. But, actually, I have an even better plan, which is don't do anything now. That's 2 times 1. And then I'll just do it all at the end. 2 times 1 plus 9. That's 11, worth the reward of 16. Okay, that's a good plan. So we now get to the final week of the class, or 1 week to go. Well, the only way I can pass the class is to do both projects. That's what, according to our data, 2 times 9 is 18, actually not worth the reward of 16. And so in week 2, you say, with no projects yet done, you say, actually, this class was probably never worth signing up for in the first place. It's just so much work to do both these projects, and you drop the class without ever finishing it, right? And so you kept thinking that you had a plan, but the plan kept morphing, right? And that's what the present bias is doing. And so even just this almost purely mechanical agent following the simple, arithmetic rule is in a sense reproducing the phenomenon that we kind of, know from our own experience that actually happens. And so how do we help the student deal with this? Well, we could just delete 1 node from the graph. We say, all right, you cannot reach week 2 without having done a project. In other words, that's just a different way of saying project 1 is due by week 2, and you have to do both of them by week 3. Now the agent, again, procrastinates. They say, well, my plan is to go here and then do 1 each week. But now when they get to this precipice where they were about to go wrong, we don't let them go wrong. We say, at least 1 project is due now. And so they have to do that. So 2 times 4 plus 4 is 12, still worth finishing the class. And they successfully get all the way to the end. Okay. And so the point is almost not, this particular example, but how mechanically, we could just create this example, and it sort of recapitulates the story of somebody procrastinating and ultimately not being able to finish a class. And the way we could intervene and actually help them by reducing their freedom of action, right? This is sort of, in the end, what we mean by a behavioral agent operating in an algorithmic environment, right? We're modifying the environment, in this way so as to help the agent complete things. And so one question you could ask, a very natural algorithmic question, on which there's now been, some amount of progress. So over these past few years, I give you a directed graph with costs. Is there a subgraph that the agent will complete, right? A kind of motivating subgraph. I put this example here. I won't walk through the whole thing, but it's an example just to show that actually sometimes there's a subgraph, but no path is actually sufficient. Sometimes in order to motivate the agent, you actually need something richer than just a path. And so this problem of which this was an instance, right? Deleting this node produced a subgraph the agent would complete when the full graph was something that they wouldn't complete. This problem turns out to be NP hard. And actually, if I want to figure out what is the minimum reward I would need to produce a motivating subgraph, this nice result of Albers and Kraft from a few years ago shows that there's actually no way to approximate better than square root of n. There's also been some fixed parameter tractability results looking at, for example, characterizing things by the number of branch nodes, right? So this graph has one branching node in it, but otherwise it's almost path-like. And we can, of course, consider other interventions. I don't necessarily just need to delete nodes. I could, for example, simply increase the cost, make certain things more expensive, and then sometimes we recover reasonable approximation algorithms. Okay, so this is sort of a rough idea of what I mean by a behavioral agent operating in an algorithmic environment. And some of these stylized examples evoke things that we can picture from our own experience. I want to now sort of launch into a somewhat more complex example, again, presumably familiar from most of our experiences, in which we have an agent operating under a form of present bias, a bias in which they're viewing the present differently from others, in which we would like to somehow intervene to actually help them achieve greater utility. And that story is the story of you scrolling through a social media feed, right? So this is now going to come out of some work that Sendhil Mullainathan and Manish Raghavan have been doing over the past few years, starting with some, really interesting conversations with people working in social media, about the problem that there's a lot of regretful use on social media. We sort of all know what this means. We go online expecting to just spend a little bit of time. We spend way too much time. We regret the time that we spent in retrospect. We sort of ask, what do we do about this, right? It's effectively as though there's some kind of conflict within us. Part of us wants to, be online. Part of us wants to not be online. And we need to figure out how to deal with that. Right. The fact that we had to, invent a word like doom scrolling, to describe the process of scrolling through terrible news on social media suggests that part of you sort of can't stop doing this, and part of you really would like to get off your phone and, and not do this. Right. The fact that people can go online and, ingenuously ask questions like, how do I spend less time on YouTube, when in some sense the answer ought to be obvious, but in some sense the question is very difficult, suggests that there's really a hard problem here. And so there's been a number of lines of work about this over the past few years, studying just the sort of ways in which, social media consumption or internet consumption is sort of failing to bring us utility, right? And really making this point that we should think about a conflict going on within you, right? So this person who jokes about being a professional internet quitter who has advice for you suggests that, there's a split in your preferences. One set of preferences wants to use Facebook. One set of preferences wants to override this. Facebook is presumably appealing to the part that wants to be there. And, this person you're seeking help from is trying to appeal to the part that's trying to override that, right? It's not that one set of your preferences is wrong and the other is right. It's just that they're genuinely in conflict. And so when Sendhil and Manish started, and I started looking at this, we were able to draw on some, a lot of Sendhil's experience with the broader category of goods we consume that come with self-control problems, right? That's a sort of canonical theme in behavioral economics. And it involves this difference between the present, when we want to consume, and the future, when we're going to regret our overconsumption. And the planning that we do now about how to prevent the overconsumption, right? That's sort of the tension that's going on. And at some fundamental level, it's really the tension between want and should, right? If this workshop that we were having were an in-person workshop, there might be a break, that has food, and we might find ourselves staring at the choice between, eating the healthy food at the break or the not healthy but very appealing food at the break. So we all see this in food consumption. We see this more close to the context of social media in media consumption, right? You're flying on a plane, you have 2 hours, you're thinking of watching a movie. You could watch this really educational movie about a font, about Helvetica. Or, part of you wants to just watch the superhero movie, right? And the part of you that operates in the present might have different views on this than the part of you that's planning for the future, or that's looking back ultimately retrospectively on what you chose to do. Okay, so that's this sort of, want should distinction. There's a lot of empirical work in both, food and media and in other contexts that, that the arrow of time is playing a big role in this context. So, just as some examples, these past empirical studies of Milkman, Rogers, and Bazerman in the online grocery ordering domain, where we're talking about food, looked at orders, placed for immediate delivery versus further out in the future, with a manual labeling of food items that are more want items or more should items. And even controlling for things like, freshness and spoilage and all these things, they found that orders placed to be delivered further in the future tend to contain more should items, right? You order, 3 days from now, you're sure you want salad. Right now, of course, you want the chips. Similarly, before Netflix was a streaming company and when it was a mail order DVD company, looking at movies, that were ordered, to be, received 3 days from now versus eventually movies that were streamed, to be watched now, right? 3 days from now, you would like to watch the documentary. Now, of course, you would like to stream a superhero movie, right? So this again comes back to building on these frameworks that we're talking about for time inconsistency. Our preferences are not consistent across time. And this matters a lot for how we're collecting data for online platforms, right? Because a basic question these platforms have to answer is, what do users want? And if what users want is inconsistent, and if the platform can only see the clicks, then how is it supposed to make sense of this? Right? In a way, a fundamental principle of user modeling is the principle of revealed preference, right? The principle of revealed preference says that people choose what they want, so choice must reveal preference. And obviously, a lot of work in behavioral economics sort of could be viewed as sort of a challenge to the principle. Right? It's not that revealed preference, is necessarily always right or always wrong, but rather we need to be careful about when we're applying it and when we're not applying it. But certainly, it's very much the case that the whole premise of recommender systems is that, the whole premise of recommender systems is that clicks are what we have access to, right? We have the hard problem of inverting a mental state that we can't see what you're thinking as you do these clicks. But what we have is the clicks. We have an enormous number of them. And so whether revealed preference in our context leads to the correct conclusion really depends on what it is that's being chosen, right? It's not, in the same way that we can't say all food comes with self-control problems or all food doesn't. All of social media does not come with self-control problems or not. It depends on the particular kind of content. And so that's really the kind of question that we have to ask, right? When does this, what insights does this inform about platform design? And so in that sense, I want to talk about a sort of simple model of social media consumption and how we might reason about it. Okay, so let's go back to this picture of you scrolling through your social media feed. Start with let's take the most simple model, just so we can look at it in sort of real time here. Imagine a user is consuming a linear content feed, and their main decision is just whether to continue on to the next item. And again, they have these two conflicting sets of preferences, one of which operates in the present, one of which is able to plan, right? So this, in the same sense that we had this split in preferences in some senses, we're doing graph traversal. So here we'll call them system 1 and system 2. System 1 and system 2 are kind of two characters that populate the landscape of behavioral economics, show up in many places. Here we're really just going to use it in the narrow sense of system 1 acts first, it's impulsive, it operates in the present, system 2 is capable of planning. And we'll think about the story here from the perspective of system 2, which is trying to decide, like, do I even want to be on this platform in the first place? Okay, so here's how the two interact. So system 1, it sees a piece of content. With probability P, it acts first. And with probability P, it's engaged, it's interested, it continues on the next item. With probability 1 minus P, it loses interest and hands control to system 2. Now, system 2 uses long-range planning. So it's looking at a piece of at item T, and it gets some utility V sub T from it, which let's say comes from a distribution with mean V bar. Now, system 2 also has some outside option for leaving the site and getting on with, you getting on with the rest of your life. So the net utility from item T is really VT minus W. Okay, so utilities of future items are known, distribution is not. Now, if I just had this, I wouldn't be able to explain why a user would ever leave the platform, right? Because if V bar is less than W, you shouldn't be there in the first place. You're getting a net loss with every piece of content you consume. And if V bar is bigger than W, then you're getting a positive net utility. And so why would you ever leave? You're just harvesting positive net utility. So we need to add one final ingredient, which is some notion of satiation. Okay, and so one simple formulation of satiation is just a probabilistic one, right? That there's diminishing returns for the content. In particular, we could model that just to be able to do calculations here in the simplest possible way, that at some random point in the future, system 2 will satiate. It's going to be full. It's like, I'm done. I'm not going to receive further utility. So each step with probably Q it wants to continue, with probably 1 minus Q it wants to stop. And so its interest undergoes a single on-off transition. We could also model this with sort of deterministic exponential decay in the utility received. We get similar results. Okay, with a couple of wrinkles differently. Okay, so given this, we now actually have a fully well-defined decision problem, right? System 2 is standing at the edge of the social media platform, right? They haven't yet opened the app on their phone. They're saying, do I want to go look at Instagram today, right? Or do I want to go on YouTube today? Or do I want to go on TikTok today? And that's a planning problem. They have to ask, will this session produce positive net utility for me? And the way they have to reason is, V bar is bigger than W. So I'll be getting utility for a while, but at some point I'll want to leave. And then system 1 is going to be impulsively consuming things, and I'm going to be wasting a lot of time. And will that actually burn off all the utility which I acquired, right? That's effectively, in sort of a slightly more elaborate way, a sort of calculation that we intuitively do, potentially multiple times a day as we pick up our phones, right? And we have enough ingredients here in the model to actually calculate, right? Because we have these 3 things. We have the value for the item. We have the satiation parameter Q. We have the sort of moorishness, right? The probability P that system 1 is in control when consuming a piece of content. And as a function of those 3 variables, we can now figure out what is system 2's planning problem. So system 2's planning problem, in the sort of simple form that we've set up here, it just looks like it has, it's a continuous stream of items that you're consuming. And we want to just figure out the total utility at the end. Now, for analysis point of view, we could divide, really it's just this unbroken set of consumption decisions. We could divide it into 2 phases conceptually for purposes of analysis. Phase 1, before system 2 satiates, when they're still getting value. And phase 2, after they satiate, when now they just want to leave and are losing value, right? Because they're losing their outside option for every step that they're there. Okay, so phase 1, what's happening? System 2 is collecting V bar minus W utility and expectation every step, net utility. And my simple probabilistic formulation is actually memoryless, so we can do this calculation very easily. If we were doing deterministic satiation, we'd have a slightly more bookkeeping to keep track of, but it'd be fundamentally the same thing. But in our probabilistic version, the expected number of steps left in phase 1 from any point is just 1 over 1 minus Q. I'm just waiting for this satiation random variable, with bias Q to come up tails. And that takes time 1 over 1 minus Q. So the expected utility from phase 1 is just V bar minus W per step times 1 over 1 minus Q. Now we get to phase 2. System 2 is full, it's satiated, it would like to leave, but it doesn't get to leave until system 1 stops mindlessly clicking. So it collects minus W per step from the loss of the outside option. But the user remains as long as system 1 is there. And the expected length of that time now is a coin of bias P that has to come up tails. The expected length is P over 1 minus P. Right, that extra factor of P, because system 2 might luck out and actually system 1 wants to leave immediately, so it could have length 0. So we put these together, and system 2's utility is actually this random variable with expected value from first phase, V bar minus W over 1 minus Q, minus the value you lose in the second phase, P W over 1 minus P, right? So constant over 1 minus Q minus constant over 1 minus P. And of course, it's the max of that with 0, because if you could also just choose not to go on the platform if you expect to get negative net utility. Now, that's what the user thinks. But again, as with our previous examples, there's the problem of inverting a mental state that we don't have access to. The platform just sees clicks. It just sees the length of the session generically, right? Barring further instrumentation, barring surveys, it's the default thing it sees is just clicks. And the length of the session is just the length of the 2 phases, 1 over 1 minus Q plus P over 1 minus P. Right, and this is the wedge that opens up between utility on the one hand and engagement on the other hand. Right, they both have 2 terms that look similar, constant over 1 minus Q and constant over 1 minus P. And they agree on the first sign, but they disagree on the sign of the second one. Right, and so that's essentially where this knife edge opens up, right? This gap opens up between, right, what users were sort of hoping to accomplish in social media and what they end up accomplishing. Right, in a world where P equals 0, we don't have second terms. Right, so if we didn't have a behavioral bias, utility would grow monotomically with engagement, and measuring engagement would be a good proxy for utility. But if P could come from a large range of possibilities, then engagement is not necessarily a proxy, right? If the platform sees a long session, that long session could come because the first term is large and the user is getting a lot of utility, or it could come because the second term is large and the user is actually losing utility. right? And for a large enough P, the user might just decide not to visit the platform whatsoever, okay? So in some sense, if the platform, even a platform that, isn't, say, driven by a profit motive, right, that just wants to, create content that will make users happy, even in that ideal situation, right? Or say you're building a browser plugin that you yourself wrote to help you with your self-control problems, that too, the altruistic platform, the browser plugin, no matter how much it's trying to help you, it faces a communication problem. It doesn't know your mental state. It just sees clicks. And so if it's trying to say, decide what kind of content to recommend, it's choosing in PQV space. It can measure engagement, but not utility. And essentially, like, going back to these equations, imagine that you had this dial that you're turning that's controlling the mix of content. As you turn the dial, you're like, oh, this is good. Engagement's going up. But I don't know whether the dial I'm turning is raising P, is it raising Q, is it raising V bar, right? From the engagement signal, I can't actually tell. And so you can get situations where the user is more and more engaged. You're like, I'm making them happier and happier. And one day they just don't come back at all. And it's because the dial you were turning kept cranking up P, making the session longer and longer, burning away more and more utility until finally this number became negative. And one day the user wasn't there at all. Right? And that's kind of the challenge that we face when we're trying to design these systems. So let me talk about just the there are a lot of design principles that come out of this, right? That fundamentally, this model is arguing that revealed preference is insufficient to capture what's going on. If we want to really reason about the data that we're collecting, we need to think about this language of utility and the tension between, system one and system two. And so I think, although, in this sort of quick overview, I can't go into all of the issues that come up here, it's a language that allows you to think about a bunch of design choices. The one I've been talking about, which is how to interpret the data we collect, as well as other things like the role of surveys. Like a survey, on YouTube, suddenly it pops up, how are you enjoying YouTube today? Please rate from, very happy to very unhappy. That's essentially the platform reaching out and trying to say, could I please speak to system two directly? Yes, I'm collecting your clicks, but I'd like to know, something about your mental state. My model here that I've been talking about talks about just scrolling through a linear feed. But obviously the number of options that you display, right? Having branching choices can affect this, because more ways to collect utility, also more ways for system one to impulsively be engaged. Things like the benefits of enforced breaks, right? So we see sites like YouTube, Instagram, TikTok introducing features that you can actually set in your profile, saying like, I would like every 15 minutes, for the thing to actually pause for a minute, where I can't do anything. And you could ask, why is it that a platform like TikTok or Instagram that's all about keeping you engaged, why would it give you the option to introduce a minute of pure boredom where nothing's happening every 15 minutes or every half hour? And the answer is, if you are sort of, it's because they also are beginning to reason about this problem of lost utility, right? You need to be able to promise the user in a way that you can commit to that 15 minutes in, system two will predictably be back in control and can make the decision to leave the platform, right? And without that, people may not ever go there because they know that they're just going to spend too long. Okay, so a lot of design choices that we can talk about in this space. All right, so in the spirit of this quick overview, I want to move on to a second kind of algorithmic environment, right? This whole thing has been about a first kind of algorithmic environment where the algorithm is serving you choices, right? It's creating, in our first example with graphs, it's creating deadlines by which you should do assignments. It is showing you particular kinds of content that engage you in the moment or in the long term, right? It's creating the world that you operate in. And we're asking, the question, if people have behavioral biases, how to create the world in a way that's going to work well with those biases, where those biases won't cause the user to lose all their utility, but instead will channel that in a reasonable direction. Let me use the remaining time, this final 15 minutes to talk about this other kind of environment, this algorithmic environment that comes up, which is the algorithm is sort of down in the world with you, right? The algorithm is not, some other algorithm might be building the world, that's fine. But down in the world is a second algorithm that's your partner, right? That's operating with you, right? And so this is, again, the case of, you and the algorithm are sitting there writing text together, you're writing code together. The algorithm is there as providing a heads-up display and actually actuating things in the car, right? It's doing braking assist, it's doing steering assist, it's keeping you in the lane. You're an expert, doing medical diagnostics, triaging resumes, you have an algorithm alongside you. And again, your actions are being interleaved with the actions that it has. And when we think about these kinds of environments, we often ask ourselves, what will happen in a world where the algorithm is just better than we are, right? What are we going to contribute in that kind of a world? And those discussions often quickly lapse into the sort of, become a bit science fictional, right? Like we sort of lapse into science fiction because although it's amazing what these things can do, we're not yet in a world where the algorithm can unambiguously write prose better than we can, where it can drive a car unambiguously better than we can, where we're writing our EC submission and simply better at proving the theorems and writing the paragraphs. And we're not there yet, right? We aren't in a world yet of post-human mathematics or post-human prose writing or post-human music composition. Obviously that animates a lot of our discussions, but it would certainly be interesting if we had a domain where, which had a couple of properties, right? One, you have people who, as with math, or as with, the composition of music, where people train their whole lives to achieve a level of mastery that inspires, a sense of awe in other humans, where you have a century or more of academic scholarship, right? Whole libraries full of books about this topic. And yet, despite all those things, algorithms have just completely eviscerated human performance. They're just light beyond where we are. And there is a domain like that, and that domain is chess, right? Chess has sort of long been this challenge domain for AI. It's a thing which obviously humans take very, very seriously. It's something which sort of many, famous people in the past, I mean, this is an array of photos that includes, Herb Simon and Alan Newell. It includes Claude Shannon in the upper right, along with Feng-Cheng Xu, the creator of Deep Blue. It includes Garry Kasparov, the world chess champion. A lot of, people on both the chess and the algorithms and the math and the economic side have thought about chess. And it's a domain where, despite all the human expertise gone into it, algorithms are just better, right? The singularity arrived in chess in roughly 2000, 2005, right? So long history of thinking about this, right? Chess has the interesting feature of having been called metaphorically, the Drosophila of multiple fields, the Drosophila of psychology by Herb Simon and William Chase, in the 70s by John McCarthy, the Drosophila of artificial intelligence. And now it's sort of the Drosophila of something else, right? It's the Drosophila of machine superintelligence, right? The thing that we fear could happen in math or poetry or music has happened in chess. Because, we sort of all remember, maybe, the story of Deep Blue defeating Garry Kasparov, the world champion, in 1997, and that was viewed as like the moment that, the machine beat the human. But that was still a moment when the two were really battling on roughly equal terms. The machine just kept getting better. And so the last time a human ever beat a full-strength chess engine running on a desktop computer was 2005. By 2007, they could beat the top players, even if they, gave away, pawns or even knights or bishops at the beginning. And they just kept getting better from there, right? 2018 was sort of this, breakthrough, which sort of brought deep learning into play on this with AlphaZero from DeepMind, which trained itself purely from the rules of chess and became incredibly powerful, right? And AlphaZero was reproduced by the open source community as this engine. Leela, and another way to sort of think about the sort of light years beyond that this thing is to think about sort of, a sort of reasonably competent human player might have a chess rating of 1100, strong amateurs have 1800, super strong amateurs have maybe 2300. The best players in the world are 2800, and the best chess engines are now far beyond 3300, right? They're as far beyond the best players in the world as the best players in the world are beyond, amateurs who are just, sort of into the game as sort of as a non-professional pastime. So with, and this is joint work with Ashton Anderson, Kareem Hamadeh at Toronto, Reid McElroy-Young, who was a student in Toronto, now a postdoc at Harvard, Sid Sen, who's at Microsoft Research. We were looking at this, and we were in particular intrigued by this as a kind of just model system for studying AI dominating in a field where humans are experts. And we were also, once Leela was available, you could actually take the deep net behind Leela, this incredibly strong chess engine. And you could ask, what else could we do with Leela? Could we create an environment in which we could try different configurations of stronger and weaker agents interact with each other? And it felt like it'd be useful in a situation to have something that could be a metaphor for the role of the human, right? It'd be fascinating to sort of put humans into these situations. But even with all the games that people play online, it's very hard to create a sort of training loop that involves humans. So the question is, could we create things that try to simulate the behavior of humans? And so the idea that we had was take the power of Leela, but put all of that power not into making great chess moves, but into making human-like chess moves. Okay, so can we learn to match human decisions in just arbitrary chess games? So the idea is, I'm given a chess position P encountered by a human player of ELO rating X. Don't try to make the best chess move as Leela would make, but instead try to predict the move that the human would make. Okay, so we took, now one thing about chess that's nice is there's huge amounts of data, and it's sort of by definition completely public because people play online, people release all of their games online, right? So like you go onto a site like Lichess, for example, all the games are, completely open and public. You have hundreds of millions of games played by humans of many different ratings. So lots and lots of training data on which to try taking positions, and so take the Leela architecture, but there's a head on top of Leela, on top of the deep nav Leela, which is trying to make the best chess moves it can, right? And you sort of rip that head off and you rip the top layers off and you put in a new head with a different objective function, which is to try making the move that a human of ELO rating X would make, right? And again, ratings are sort of as we had, so we could try to have a rating, match a human of rating 1100, match a human of rating 1800. We could pick any rating we wanted and try to say what would a person with that do, okay? And so we trained a chess engine, which we called Maya, on hundreds of millions of human games to do this. Now, what would it mean to succeed at matching moves? Well, you would want to sort of have a version of Maya for each human rating X. If you looked at the move matching accuracy, then the one that's trying to be 1200 would sort of peak in its accuracy when it's given a game from someone, a player of rating 1200. It would be less good at matching moves played by people of other ratings, and the one that's trying to be 1800 would have the most accuracy when you fed it, questions involving moves made by people rated 1800 would fall off after that. Okay. And so we can actually look at how this, and so this actually you can do quite effectively. So there's just a quick plot showing on the x-axis the rating at which we were testing the prediction algorithm. This is Maya's predictions of what the next move will be. Maya trying to match an 1100 player, 1300, 1500, 700, 1900. And then you can also try to predict moves just by sort of weakening Leela or weakening a sort of traditional chess engine like Stockfish, which is sort of one of the kind of peak, the sort of pinnacle of the traditional chess engine world, and just tell it, we're going to limit your search depth and then just try to make a move. Right? And so if I can weaken the chess engines and they'll play at weaker ratings, but they won't really match what humans are doing, whereas Maya actually matches what humans are doing. Okay. All right. So, so we can say, you can actually watch as sort of Maya at different strengths discovers, different moves, right? So like, in a chess position like this, there's this tempting bad move B6, which weak players tend to find, and then there's a bear move B takes A6, and the different Mayas will differentiate, right? The chess engine will just play the good move, but the weaker engines will play the tempting human move, and the stronger ones will play moves that better players don't. So we released this on Lichess, where Maya is now actually the most played bot on all of Lichess. It's played several million games over time, right? Because it's a bot where it plays you on roughly equal terms, but not just by artificially weakening a super powerful engine, but by actually playing human-like moves, okay? So you can go on Lichess want to do this. But I want to use this as an environment in my final few minutes for talking about an interesting question that comes up, which we had sort of, for a number of years, wanted to think about. And once we had Maya, we could finally ask this question. And the question is, when we have these human algorithmic hybrids, right? So you're working side by side writing code, you're working side by side writing text, you're in the car and the thing is doing lane assist and steering assist and braking assist. There's a certain danger that comes up with human algorithmic teams that we sort of intuitively fear, which is the sudden handoff from the algorithm to the human, right? The algorithm is basically doing stuff and suddenly it hands things off to you. Now, there are a lot of reasons why sudden handoffs are dangerous. One is just you weren't really paying attention and suddenly you're supposed to do something. But there's a more subtle danger. Even if you are paying attention, right? The algorithm might be driving along. And again, because we're not in the world of chess where we really have strong algorithms, let's lapse into sci-fi briefly. I'm in a world where I really have autonomous vehicles that are very good at driving. And the thing is driving along using the laws of Newtonian mechanics to do a bunch of stuff that humans would not be very good at and wouldn't really be able to control the car. And suddenly, for some reason, the algorithm starts buffering. It loses its network connection. It crashes. Who knows? Metaphorically crashes. And suddenly, I have to take over. But I don't know how to drive in the state that I'm in. I would know how to drive if I'd been driving all along. but it's doing some weird Newtonian curve around some other car, and I don't know how to take over. Similarly, you know, I'm a customer service agent where I'm doing some negotiation, and my sci-fi chatbot assistant is doing this great job of negotiating in a way that I wouldn't, it's not how I would be doing it. And suddenly it starts buffering, it pauses, it hands it over to me. I don't know how to take over from here, right? This is not what I would have been doing. So the better design, if we think about this, we really want an algorithm that has two things. It's powerful, but it stays in states where a human would know what to do if they had to take over, right? It's a kind of interpretability problem, right? The super powerful algorithm might be wandering through some uninterpretable part of the state space. So if I had to take over, I just wouldn't know what to do. Or could we find something almost equally powerful where I would know how to take over, right? A kind of interpretability through your actions. So again, this is the kind of question that we had wanted to ask. And we thought chess is finally a domain where we could ask, could we try to achieve this design goal, right? This notion of to alleviate the danger of sudden handoffs, right? It's a thing that we intuitively fear. I mean, I draw you pictures here of like, you know, maybe you fear it with, you know, your paired programming assistant, maybe even more your self-driving assistant. I think, you know, in fiction, we see lots of cases where we also fear it, right? So, you know, I was sort of thinking about all the intuitive ways, you know, for those of you who have read or seen Lord of the Rings, there's kind of this, we keep repeated frustrating moments in Lord of the Rings where there's this group of people on this very dangerous adventure, and they're like, we're good because we have Gandalf, the all-powerful wizard, with us. But somehow Gandalf keeps mysteriously vanishing and just leaving them to fend for themselves, right? So Gandalf gets them into a situation that they wouldn't know how to handle on their own, and suddenly Gandalf's off to fight Saruman or do whatever Gandalf is doing. And suddenly they flail as they have to fend for themselves, right? There's been a sudden handoff. Similarly, like for those of you who have seen the Wizard of Oz movie, this screenshot kind of captures the tension of the opening scene. You can sort of read on Dorothy's face, like, it's terrifying to deal with the Wicked Witch of the West, but at least I have Glinda to help me. Except Glinda 2 minutes later mysteriously vanishes, leaving Dorothy to fend for herself, right? And so I think this notion that we have an all-powerful entity helping us, and then suddenly it's not there, is a thing that is sort of, it appeals to certain basal fears that we have that come up, once again, with AI. So that was the question that we wanted to ask. And we can actually create a handoff experiment using chess, and then ask, can we design a powerful engine in chess that actually is going to be better for this handoff, right? So here's the experiment that we set up. I'll just describe my final few minutes and then wrap up. So imagine a version of chess, and sometimes humans actually play this game. Humans are different strengths, but we'll do it with, imagine Leela and a human play Leela and a human, okay? So there are two teams. And the way they do it is Leela and the human are on the same team here on the left Leela, left human. They can't communicate. And the responsibility for the next move is determined by a coin flip. Okay, so on every move, it's either Leela makes the move or the human makes the move. And so when you actually have situations like this, you know, you can actually play this game. Leela will do some brilliant thing like it will sacrifice a rook because it sees a winning attack. On the next move, the coin comes up tails and the human has to move. They have no idea what to do. And they make some bad move. And now Leela's like, what did you do? Now we're just down a rook. The attack is gone and I sacrificed a rook for no reason, right? You see the same thing with Maya, right? So obviously with human and Leela, we can't play hundreds of millions of games. With Leela and Maya, we can, right? So we have Maya as a stand-in and we see the same problem. Leela makes a brilliant move. Maya has no idea how to follow up on it and the partnership loses, okay? So the question we asked ourselves was, could we create a better version of Leela for this purpose, right? It's not gonna be better than Leela at chess. It's gonna be better than Leela at this task, right? So we create a training loop where we create something called, let's call it a partner bot. And the idea is it's trying to win chess games in a world where it gets to move with probably P and Maya gets to move with probably 1 minus P and they can't communicate. So partner bot has to make good chess moves because it has to win against a team of Leela and Maya, but also it has to stay in a part of the chess search space where its moves are gonna be so transparent what it's doing that Maya will know what to do if it's Maya's turn next, okay? And so we created this training loop, and it turns out that you can actually build bots that actually have this property. And so this is work that's going to be appearing at iClear this summer. But effectively, what happens is what you actually hoped might actually happen, which is if I look at, okay, let's consider engines that I could put in this upper left corner to team with Maya against a Leela Maya team in this sort of stochastic partnership, right? Where each one is making a move with some probability. Okay, so obviously Leela Maya versus Leela Maya, well, so Leela here is going to have a win rate of 0.5 because by symmetry. The partner bot does better than that. The partner bot in Maya beats the Leela Maya team roughly 66%, 0.5% of the time. Actually, we're counting draws also. So what this really is you get 1 point for a win, half point for a draw. Now you could ask, maybe it's just that what we need is two parties that really understand each other. So we could ask about a Maya-Maya partnership. That just gets crushed because when you have Leela on the other team, even when it's really not communicating well with its Maya partner, it still beats Maya versus Maya. So the point is this partner bot has to do two things. It has to be strong at chess, but it also has to be a good partner. The other thing is we can now take each of these bots and actually just do them in solo competition versus Leela, the super powerful thing. Again, Leela versus Leela is 0.5 by symmetry. The partner bot plays reasonably strong chess, right? To even draw ever against Leela, you have to be unbelievably good. Humans can't do it. So the partner bot, gets a point score, right? So it's some mix of occasional wins, some frequency of draws to get sort of an average of 0.14 points, right? We're half point for draw, 1 point for win. Right, so better as a partner, weaker at chess, but still reasonably strong. Maya, of course, gets crushed by Leela. Okay, so the point is, this sort of thing is possible, right? And we sort of feel like this is the sort of a fascinating framework for thinking about this in other contexts, right? In the context of writing or coding or autonomous driving or any other place where we have interleaved actions between humans and AI, to think about this kind of transparency in actions, right? Create a powerful entity, right? This partner bot is the fact that it can be even weakly competitive with Leela means it's very powerful at chess, but also is better as a partner, right? Its moves are more transparent, right? A kind of interpretability that's not about verbally explaining what you're doing, but about making your actions transparent enough that a weak partner can take over from you. A bunch more to say here. I'll wrap up. So really, this has been all about creating environments where computation can provide assistance to behaviorally limited agents. Right, our behaviorally limited agents may have suffered from present bias, from impulsivity, or in this last case, simply from cognitive limitations. We're just not smart enough to search the whole game tree of chess. And so there's these sort of broad questions, which I think are going to lead to a lot of interesting sort of directions for follow-up, right? How do we algorithmically construct environments where the behavioral agent can maneuver within it to achieve high utility? How do we take algorithmic actions in those environments that are likely to be compatible when we interleave them with some behaviorally limited agents? And so this idea of behavioral agents operating in these increasingly complex algorithmic environments with increasingly complex algorithmic partners is really a very rich sort of thing to think about. And I think it's going to lead to really a lot of interesting questions going forward. Thanks very much.